This part of the review for the exam is going to be based on the interval of convergence problems at the bottom of the screen here. This is an important idea when we're studying power series because this is really the equivalent thing of finding the domain of the function. Interval of convergence means finding which values of x you can plug into this infinite polynomial so that the resulting series actually converges to a finite value. In other words, these are the inputs that you can use in these things as functions where you actually go get an output. So that's exactly what our definition of domain is. The other reason it's important is that it's always based on the, well, we are always going to base it on the ratio test. There are some other ways to do it, of course, but with the ratio test, hang on. If we can use the ratio test for this, then this also will increase your understanding of what the ratio test is doing. So let's use as an example, the example I did on Friday was this series, and we referred to these guys in here as a sub k's, like we have in the before. Notice that these are not necessarily all positive values like we had been using before, because depending on what value x is, you could have negative numbers here. So for example, for this one, if you plugged in like x equals a half, then you're going to get an alternating series. So so the a sub k here, the assumption is not that it's always positive. Notice that there's always one example that you can always give for an x that you can plug into the series, and that's the one that makes all the terms zero. Notice how the powers that are the powers that are going on here are all powers of x minus 1. So for example, if you let x equals 1 in this, the series is going to be, it'll be 0 to the first power over 1 plus 0 to the second power over 2, and so on. So that will definitely converge to 0. And so there's always one value that you can plug in that will make sure that will make the series converge. And anyway, in that series, the number you plug in to get all zeros in those powers is always going to be the center of your interval of convergence. So you're basically locating the center of the series when you do that. Anyway, back to the ratio test. So the ratio test says that I should be able to look at this limit, and we've seen that when that limit, the denominator is easy to write down because it's literally just the AKs. So it's going to be exactly what you see in the problem here. AK plus 1 requires a little bit of care because we need to take the thing that's circled up there in green, we need to change all the k's to k plus 1s. And so for some problems, that's easy, and for some problems, it's a little more challenging. But in this case, that's what we would get. So we always get this stacked fraction when we're doing the ratio test. And so we always resolve it the same way. We make the stacked fraction become a product of the numerator times the reciprocal of the denominator. So it'll look like that. The one piece of algebra we'll always get to do is resolving the exponents in whatever thing with x's is being raised to a power, which always has to be there. These are called power series because they have powers of x in them. So you always will have powers on the x terms that that you can resolve. So this these two powers together, they both, when we have a power of something, it's really repeated multiplication. And so what I really have there is a bunch of copies of x minus 1 being multiplied together in the numerator and the denominator. And so every common copy of x minus 1 is going to cancel out. The denominator has k copies of x minus 1, and the numerator has k plus 1 copies of x minus 1. So when you cancel, the smaller power is going to be gone entirely, and then the larger power is going to be mostly gone, and we have to just think about how many copies of x minus 1 are left after I've canceled out the ones from the denominator. And in this case, there'll be one left. There was one addition. There was one copy of x minus 1 in the numerator more than there was a copy of x minus 1 in the denominator. And so that's the only algebra that's actually going to happen here. Now, one thing that does happen with this ratio test calculation with a power series is that it's a little confusing because you'll have two variables. You'll have an x minus 1 and a k running around. And so my suggestion is just take a step with all the crossed out circled stuff to write down what you have, where you're separating out the effect of the x minus 1 from the k's. So that's what I have. It's equivalent to what I have. And I've separated all the stuff with x's away from all the stuff with k's. The reason that matters is that the limit here is happening only as k goes to infinity. The limit has nothing to do with x. X is a fixed number, fixed unknown, but it's k that's getting larger and larger and larger. So when k is a million, a billion, a trillion, only this term is changing. This would stay the same. So as k goes to infinity, this thing in parentheses is going to 1. And the x minus 1 part is not changing. So the long and short of that is that the answer to this limit is just x minus 1. In the ratio test, this is our r. So remember that the ratio test says if r is less than 1, and I'm actually going to update that. The ratio test that we did was only applied to positive series, and like I said at the outset, these series may not be positive. So the more general statement about the ratio test is that if the r is between minus 1 and 1, then the original series converges. So in this case, the r is x minus 1, and so I can add 1 to everything in that inequality and rewrite this as if 0 is less than x is less than 1, 2, then the series converges. So the only algebra I did there was taking this inequality and then adding 1 to each of the three parts of the inequality, and it gave me this. So I can see here, this is the sort of the core of my interval of convergence. As I expected from up here, x equals 1 is right in the center of this interval. So I knew that was going to happen. We're not quite done yet because this is true. The ratio test did tell us this, but the ratio test also allows for the possibility that this series converges when the r is equal to 1. The ratio test is inconclusive then, but that doesn't mean that that we can't know what's happening when the r is equal to 1. And again, from the more general statement would be when r is 1 or negative 1, when you're out at the edges of this thing. So in the video we did before on this stuff, this is called checking the endpoint. So we see that the interval here is everything from 0 to 2. The ratio test is not conclusive about x equals 0, and it's not conclusive about x equals 2. So what I have to do is go back and just check those some other way. I'm going to check those with some mechanism that I know that does not involve the ratio test. So let me get rid of this. I'll just do that up here. So I'll make a note what I'm doing. I'm checking the endpoints. And this is never, not hard to do. The biggest problem people have is they just forget to do it. So the two endpoints are x equals 0. That's one of the endpoints of my interval. And so the way I check that is by just literally plugging in 0 for x into my original series. So I have series k equals 1 to infinity, 0 minus 1 to the k over k. So literally the original series with 0 in place of x. This is minus 1 to the k over k, and that is a convergent alternating series. So the negative 1 to the k means it's alternating. The fact that the terms go to 0, the 1 over k's go to 0 as k goes to infinity, mean that this is a convergent series. Remember, that's only true for alternating series. So this is a convergent alternating series. And the reason, I don't have room here, but the reason is because the terms go to 0. That's sufficient for alternating series. The other endpoint was x equals 2. Remember, this was my range down here, 0 to 2. So when x equals 2, I have the series 2 minus 1 to the k over k. And so that looks like that. That's our friend, the harmonic series. That's a p series where p equals 1. So this is divergent. So this is a divergent p series. And again, if you don't remember which p series are convergent or divergent, the important thing to know about p series is that they're easy to check with the integral test. So worst case is you would go look at the integral of 1 over x and realize that goes to infinity, and then therefore this series diverges. So in our endpoints, one of our endpoints gave us a convergent series, and one of them gave us a divergent series. And so now I'm ready to write my final answer. These numbers are my core, but also x equals 0 made this converge, but x equals 2 did not. So the final answer is 0 less than or equal to x less than 2. In other words, it's exactly that same interval, but with 0 thrown in, because I did get convergence for 0, and without 2 thrown in, because I definitely get divergence for x equals 2.